what I'm going to do is I'm going to start with a video that probably doesn't look like it relates at all. About 15 more seconds. So we see things like that, and people will frequently say, wow, they're like a machine, all right? And I like that because you see a lot of parts moving around. They all seem to be moving together to accomplish something. There's a sense of timing involved, that the right person or the right part is going to the right place at the right time. And when you say it, you describe them as a machine, it has a very positive connotation to it. It's not always positive. When I got dumped in 11th grade and Diane compared me to a robot, I don't think she meant that positively, but then I asked her, you mean a Cincinnati Millicron? She said, no. So you'll hear me use the words mechanism and machine interchangeably, and the words aren't interchangeable, but for the context of what we're doing here, I think that's fine. And what I'm going to do is I'm going to walk you through a quick example so that I can get to all the words in the title. And in fact, this was the very first one of these that we actually designed from the ground up. And so what we have here is any place where you see one of these black circles, there's a hinge there. We call it a revolute joint, but it's the same as your elbow, the same as a hinge in a drawer. It just allows two things to rotate relative to each other. So yes, this thing's loaded with hinges, all right? And I'm not even pointing to all of them, that's just most of them. All right? And then it has bodies in it. And so the gray one, the light grays, those are bodies. The dark grays, those are bodies. All the black ones, those are bodies. You can call them bodies. You can call them links. If you need to, just think of it as a piece of steel, all right, that happens to be in there between two hinges. Okay? It just holds those hinges at a fixed distance. And so you see this thing's not only loaded with hinges, it's also loaded with bodies. And now what I'm going to do is I'm going to take that link right there. I'm just going to grab one part. I'm going to take that part, and I'm going to pull it around. I'm going to rotate it. And what happens when I do that is all those links perform kind of a dance. They go from a U shape to a D shape. I don't know where we got those two letters, but anyway, we move from a U to a D, and now we have all the pieces in place, all right, for the title to make sense. So what do we mean by complexity? Well, just cripes, those things have a lot of moving parts, right? I'm only going to show you machines that we've put a bunch of parts in. We'll simplify it halfway through the talk, but it's mostly going to be a lot of moving pieces. For simplicity, yet everything happens with very few inputs, all right? And the point being made with this example that for that whole U to D transition to happen, it was just a matter of taking one link and pulling it, and the rest of the system came along for the ride. Okay, the elegance of, that translates as is. And after the fact, I realized, after I turned in my talk, that I should have emphasized the systematic design of, because I'm going to show you a lot of things that have a lot of moving parts in them. But the truth of the matter is, if you Google something like kinetic sculpture or kinetic artwork, you will find some great things. You will find things with tons of moving parts that do all kinds of intriguing things. But that's part of what we're after, but what we're after is being able to have systematic design approaches to doing these things. And so finally, variable geometry mechanisms. This one doesn't have too clean of a definition, but it's machines with the proper arrangement of many bodies contributing to the use or purpose, rather than just an input and an output. So for example, the U and the D, there were many bodies along that chain that had to move from the U shape to the D shape for this thing to do the job. Classically, mechanisms are designed just to relate an input to an output. You push your accelerator down because you want your car to go faster, all right? But this, we're trying to get many things to happen together. So, we were fascinated with that UD problem, and so we took another stab with a fancier U and a fancier D. These are actually the UD that that match that swoosh logo we have. And the challenge to Josh on this one was to design a variable geometry mechanism that would do the UD transition, but make it as complicated as you think we can build. And so, so he did do that. And right there, that was probably the last time that crank went around. All right, and then after that, everything shattered. But so it was the most complicated thing we could build. We've tried to tackle a bunch of things with this stuff. I'll just start the videos. Unfortunately, we couldn't get the face to play, but the face is cool. It's a whole bunch of these shape variable geometry mechanisms that, and they change it will make the face change emotions. But we have a shape-changing cam. You can see the shape changer inside of it. That's a traditional machine component. That's a parabolic light reflector up there that will allow you to change the intensity of the light mechanically. And this is a seat we played with that could actually accommodate, we tried to accommodate comfortably from the first percentile female through the 99th percentile male. And so the shape change in there is pretty subtle, but it's getting there. So a little bit more practically, we've done wings and spoilers, and the idea behind the shape-changing wing is that at takeoff you have a heavy fuel load. This is for a long flight surveillance aircraft. And at takeoff you have a heavy fuel load and you need a lot of lift. And so you have a lot of curl in the wing, but with a lot of lift you get a lot of drag. And so as you burn the fuel off, you need less lift, so you can undo the curl of the wing, therefore creating less drag, therefore using the remaining fuel more efficiently, which is what you're after. So this is happening quickly, but this is over several hours of flight time. The whole idea being, well, airplanes have flaps already, but the idea is that every shape is a usable airfoil in this as it morphs. The one on the right this is a shape change, a variable geometry spoiler that we designed and built. It's actually, we sized it to fit on the smart car of the guy I was working with, but then he sold his smart car before we could actually get it mounted. It was going to be cool, but we didn't get that far. So we've played with a variety of things doing variable geometry mechanisms, but the one where we've had the majority of success or the majority of interest has been in extrusion dies. And extrusion dies are primarily plastic. You can do it to some degree with metal, but you heat up plastic and you basically force it through a fixed hole. All right? And the hole you're forcing it through gives it the shape you want. All right? And so that's a bunch of examples up there of products that have been extruded, and you recognize this. You recognize things that go around windows or on your car, the thing where the door meets the body of the frame of the car. Those are all extruded products. And extrusion is of so much interest because it is vastly cheaper than other ways of making plastic products. You can mold, but molding is more expensive and it's a slower process. If you can extrude it, you're much better off. The problem we have with extrusion is if you look at these parts, they're fixed cross-section. No matter where you cut it, it looks exactly the same. So the capacity to do things like this actively as you're pushing the hot plastic through the die doesn't really exist. So we started out very simply. I wouldn't call this a variable geometry mechanism by any stretch, but it's showing you the basic idea. Here's the plastic extrusion coming out, and we're basically transitioning from that cross-section to that cross-section. Even this is sort of a step ahead than anybody's currently doing with extrusion. Yes, this is just a CAD model. I'll get to a real thing here in a second. And so we started here, but boy, we wanted to start talking about variable geometry mechanisms to do this. And so here's one we've actually built up the prototype and we've tested this one, and you can start to see all these links in the variable geometry mechanism, but nevertheless there's nothing exotic in here. There's no exotic mechanisms in here. They're just the same things I showed you in the first slide. They're bodies, they're hinges, and in this case we have one other thing that allows us to change lengths. But we're not introducing anything exotic to try and solve these problems. Here, this one is a little bit more outlandish, but we wanted to be able to extrude a knife blade a knife handle, the handle would typically be something that you would mold, but here with the die on the bottom, there's two levers to work. And if you were to run the plastic through it and move forward and backward, you would get the left side of the knife handle, the right side of the knife handle. You could cut them up and have the full handle. So again, everything I've shown you so far is a CAD model. The CAD models, of course, are always ahead of the practice, but here's the practice. That die on the top, it's running, all right, and you can see we're changing the shape of the thing that's coming out of it. And so these are a couple of pictures of what the parts look like that we get out of it. And not too exotic yet, but we're getting there. The fact that we can do these wavering profiles is something that hasn't existed before in extrusion. And you see on the bottom, that's actually what the inside of that die looks like. Can't see inside of it on the top, but you see what all the links look like inside. All right? And so we got pretty excited about this. The students got pretty excited about it. And what do you do when you get excited about one of your projects? You make a cool video. So we were pretty excited about that one. That was our video to show it off. So that's the variable geometry mechanisms in extrusion. Another place we seem to be able to apply these ideas, and we're just getting into this, is in the area of morphometry. Morphometry being right there, the quantitative analysis of form, a concept that encompasses size and shape. In other words, I want to be able to quantitatively compare this to this, all right? And there are methods for doing it, all right? And like all methods, they have their strengths and they have their weaknesses. But in talking to the morphometry people, the idea came up, well, what about a variable geometry mechanism? Why don't we just try and solve this the same way you're solving your design problems by putting rigid links along here and connecting them with hinges, things that rotate, and things that change length, that just telescope or slide across each other. And so the problem we started with is this problem of cochlea analysis, which they're very interested in for a variety of reasons. But they are able to supply these curves for cochlea from many people. And the idea is there such a thing as an average cochlea? Can we tell a healthy cochlea from one that's unhealthy just from an analysis of the data? And so, so we made a cool video to go along with this one. And here you're going to see we have 9 cochlea that we're trying to find a single system to match. So it's going to show up here in a second. Right there. Those are all rigid bodies. There's some hinges in there. And if you look right there, you can see, and right there you can see telescoping links. They just change length, but you can see it looks organic. I mean, it looks biological. It looks like it's a living thing almost. But you can see it varying and lining up really well with these profiles. All right, and so the reason we're getting into this game is that compared to the other methods, the amount of data we need to generate to describe describe and compare these curves is very, very modest. And so small number of parameters, and they have actual physical meaning. When I say take a joint and rotate it from this to this, we can attach meaning to that. The disadvantages you saw if you're watching carefully, the other methods match curves exactly. We don't. All right, but if you're willing to increase the number of links and hinges you're using, we can ultimately match these things very, very closely. We increase the closeness of the match the more links and joints you let us use. And so now I'm going to shift gears a little bit and show you infinity chains. These aren't I'm making the point across top, these aren't variable geometry mechanisms. This goes back to the basic idea of mechanism of input versus output. But what this still has in it is the many, many, many links that we like to see for something to be complicated and cool. So the idea here on the right is you can see there's a link right here that I'm rotating at a constant angular velocity. And I'm tracking the motion that's output by that sliding block. All right, this is the basic mechanism that's used in a mechanical press. And so as you rotate that around, if I track the motion of the sliding block, I get a curve that looks very sinusoid-like. All right, so now what the one on the right is showing you, it's the scale's off a little bit, but the mechanism that goes from there to there to there is exactly the same as that one. But what I've done is I've added a bunch of links to it, and now instead of driving this one, which is the equivalent of this one, I'm driving that red one. So now that red one I take and I rotate that at a constant angular velocity. So I watch what the block does relative to this rather than this. And you see what happens here? You can see that the curve, it still has a sinusoid type feature to it, but we're able to warp it. All right? And so the idea is, well, if we can do that with the addition of one of these red units, what if I just allow myself to keep adding red units and see what happens? Can I do really complicated periodic curves? And so we went after, can we do a sawtooth? Can we just, with basic links and revolute joints and hinges, make something that generates a sawtooth curve? And so that's the basic mechanism I showed you on the previous slide. Here's where we start to add mechanisms to it. And if I add enough of them, it turns out I can start to get very, very close to it. And so we end up getting things like this. The thing that I have to convince you of, and you can see it tracking the output here, all right, giving my sawtooth, the thing you need to be convinced of is that that red link is rotating at a constant angular velocity to make that happen. If you allow me to speed it up and slow it down, I can make any shape you want, exactly. But the idea is not to do that. The idea is to design a basic machine that accomplishes the task. And so we'd never try to build this except in a CAD model, but it's fun to look at. This idea, if we use a more complicated device at the end, it turns out we can start going after very complicated periodic functions. And so here you see we have basically a sinusoid nested inside of a sinusoid. Same idea, the ending mechanism's a little bit more complicated, but nevertheless, that red link right there, I take that, I drive it at a constant angular velocity, and it produces that sinusoid inside of a sinusoid style curve, all right, completely mechanically. Again, we got excited, so it's video time. This is how you highlight the importance of research, all right? Fireworks, and a let it play for it, and a rocket launch, all right? All right. I'm running out of time. One of the things we like to do is take all these ideas and try and move them into spatial arrangements. You got to watch this. This is just a CAD artifact. Watch what happens here. We didn't build it to do that. It just decided to blow apart on its own. Fortunately, the real one didn't do that. But we like to take all our ideas and then, you know, in the device I was showing you, all of the hinges have parallel axes, so they always move in a plane. If you take those hinges and you start tweaking the axes relative to each other, you start getting things like this to happen. And so this was trying to build mechanical spirals. This was an origami. You can see this one goes, it will lie flat, but the CAD wouldn't work well when we tried to drive it there. So that's one of the directions we push this stuff off. I need to mention Dave because I'm not the only one who works on this. Dave helps me. Dave and I work together on this stuff. And I should mention that that's all the people in the lab who are currently working on these projects in some form or another. And so I need to thank them for being involved. And so now I have one more video, and you need to think back to the variable geometry extrusion dies, all right, where we shoot hot plastic through a variable geometry mechanism and make shapes. And so we've created a Christmas card. Thank you.